A warm good morning to all. I am Neethu MP, Assistant Professor, Department of Science and Humanities, Vedavyasa Institute of Technology. Here I am going to discuss about nuclear reactors. Before we are entering to the topic nuclear reactor, we need to know about nuclear fission. Nuclear fission is the process of splitting of a heavy nucleus when bombarded with a suitable subatomic particle, normally a neutron, into two fragments of comparable masses with the simultaneous release of a huge amount of energy. During fission, the target nucleus first combines with the projectile neutron to form a high-energy compound nucleus. The extra energy set up a series of rapid oscillations in it. As a result, the nucleus cleaves into two separate smaller nuclei of comparable masses. Mainly, uranium-235 is used for fission reaction. When uranium-235 bombarded with a slow neutron, the nucleus splits into strontium and selenium with the release of a huge amount of energy and also neutrons. The fission of a nucleus produces 2 or 3 neutrons, each of which can initiate another fission. These secondary neutrons may thus propagate the fission process, thereby setting up a self-sustaining reaction. It is then called a nuclear chain reaction or fission chain reaction. In order to ensure that the secondary neutrons are not lost to the surroundings and that they do propagate the fission chain, an adequate quantity of fissile or fissionable material must be available. A nuclear reactor is an arrangement in which release of nuclear energy through a self-propagating fission chain reaction is achieved at a controlled rate. The self-sustenance of a fission chain reaction and the consequent release of a tremendous amount of energy depends upon the secondary neutrons produced in each fission process. They are responsible for the propagation of the process through a branching chain of fissions. However, it is possible that some of the secondary neutrons may be lost either by leakage from the system or through capture by the nuclei of the system for processes other than fission. The minimum condition for maintaining a fission chain reaction is that for each nucleus undergoing fission, at least one neutron on the average is produced, which causes the fission of another nucleus. For any particular system, there is a limiting minimum size that is required to satisfy this condition. This is referred to as the critical size. The main components of nuclear reactors are: first one, the fuel. Mainly uranium-235 is used. Uranium-233 and plutonium-239 is also used as fuel. And the second one is the moderator. Generally, the fission of a fissile nuclide such as uranium-235 is more efficient with thermal neutrons than with fast neutrons. So a material of low atomic or molecular mass which can slow down fast secondary neutrons through collisions but has a low probability to undergo nuclear reaction with them is used as a moderator. Graphite, heavy water, beryllium oxide, water, etc. are typical examples of moderator used in reactors. And the third one is control material. In order to ensure that the fission chain reaction never goes out of control, certain non-fissile materials are used to absorb thermal neutrons. Cadmium, boron, etc. are typical examples for control materials used in reactors. Rods or strips of these materials, often incorporated with other metals or alloys, are located near the reactor core and pushed in mechanically whenever the neutron flux increases beyond a limit and then pulled out after control is achieved. The fourth one is the reactor coolant. The reactor coolant is used for the removal of heat generated in a fission chain reaction in a nuclear power plant to the site of utilization where the thermal energy can be harnessed to produce electricity or to do other useful works. Most commonly, the coolant is pumped through the reaction core to take up heat from the fission products. It is then passed through an external heat exchanger where the heat is transferred to the water for production of steam in a boiler and again returned to the reactor in a closed cycle. Typically, the pressurized steam from the boiler will power one or more steam turbine electrical generators. Liquids like ordinary water, heavy water, liquid sodium, organic phenols, etc., and gaseous coolants like air and carbon dioxide are commonly used as coolants. The last one is the reactor shield. The reactor shield is a shield covering the whole reactor, protects the person in the vicinity from hazardous gamma rays and neutrons coming from the reactor. High-power reactors generally have two shields. The first one is a thermal shield made of a few inches of iron or steel close to the core and which can be readily cooled. It absorbs much of the gamma rays coming out of the core and protects the outer shield from possible heat damages. The second one is the biological shield, capable of absorbing both gamma rays and neutrons, and usually consists of a layer of concrete several feet in thickness surrounding the core. These are the nuclear power plants in India. Usually, most nuclear power plants are located along lakes, rivers, or seacoasts because the facilities use water to cool the reactors. Nuclear plants are the most efficient sources of electricity. Nuclear power plants heat water to produce steam. The steam is used to spin large turbines that generates electricity. What happens when a fission chain reaction goes out of control? The immense destructive power of atomic weapon derives from the sudden release of energy produced by uncontrolled fission chain reaction. The United States developed two types of bombs during the Second World War. The first, Little Boy, was a gun-type weapon with a uranium core. Little Boy was dropped on Hiroshima. The second weapon dropped on Nagasaki was called the Fat Man and was an implosive type device with a plutonium core. These are the references that I used for this presentation. Thank you all.